Hey guys, so this next problem is another Norton and Thevenin problem. Here we're asked to show the Norton and Thevenin equivalent of this circuit. And you can see that this is RL right here. So the first thing I'm going to do here is I am going to remove RL from the circuit. So real quick, let me redraw the circuit. So this is 25 volts. We've got a 220 right here, a 330, 270. Here is where RL was, right here. I'm labeling that spot A and B. 1.2K, 1K, and then 1.5K. Okay. So I think I know what the Thevenin equivalent is going to look like. It's going to look like a voltage source and then R Thevenin or R Norton. They're both the same thing. So it's going to look like this. So I can choose to find V Thevenin first or R Thevenin first. I think I'm going to choose R Thevenin first. So that means if I took an ohm meter and I placed it right here with the circuit turned off, what would it read? So first off, how do I turn off a voltage source? So for a voltage source, I need to short it. So I'm going to try to do without having to redraw this circuit. So I'm just going to put this little paper here. And you can see that I have shorted this voltage source right here. Okay, so the resistance across this thing is 0 ohms. All right, so now we're going to break down towards A and B. Well, here's what I see. I notice between this spot and this spot, we've got 3 resistors in series. So that is 1.2K plus 1K plus 1.5K. So that's these guys. And this whole network here is all in parallel with 330 and this branch right here, which is 220 plus 270. So let me reduce all this. This is very ugly. So it looks like we've got 3K plus 0.7K. So we've got 3.7K in parallel with 330 ohms in parallel with 490. All right, so we've got to use this equation. All right, so let me punch that into my calculator real quick. So we've got 3,700, and that is all to the minus 1, plus 330, that is also to the minus 1, plus 490, and that's, oops, also to the minus 1. Oops, I made a little typo there. Let me do that again. To the minus 1. There we go. Close it all in, and then everything to the minus 1. I'm getting 187.21. Okay. So that's R Thevenin. Let's find V Thevenin. So that is the voltage between A and B. So if I put my voltmeter right there with the circuit turned on, what would it read? Well, you can see that if I knew the voltage across the 330 right there, then that would be the same as VAB. So let me think of the best way to do this. I think the best way to do this is going to be this. I'm going to find the equivalent resistance between here and here. So you can see we've got 330, that's this one, and it's in parallel with these guys right here, which we said was 3.7K. So let me see what that is. 3,700 times 330 divided by 3,700 plus 330. So that is 302.97. I'm going to call it 303 for good measure. So our circuit looks like this. 25 volts right here. 220. 303 right here. And here's A. Here's B right there. And this is 220. Okay, now we've got an easy problem. This is just voltage division. I want to know what's the voltage across the 303? Well, it's going to be 25 volts. That's the voltage being divided times the thing that I'm looking for the voltage across, which is the 303, divided by the sum of all the resistors in the divider. So that is 523 right there. 220 plus 303. Let's see what we get. 25 times 303 divided by 523 is 14.48 volts. And that is V Thevenin. So 14.48 volts right there. Okay. So that's the Thevenin equivalent of the circuit. Well, what's the Norton equivalent? I could go through all of this again, and this time use the Norton method where I short A and B, find the current through the short, but I don't want to make this a 20-minute long video, so I'm going to do this instead. I am going to do a source transformation on the Thevenin equivalent, which is going to give me this, which is the Norton equivalent. So the resistor value isn't going to change. It is 187.21. I just need to figure out what this current would be. How do we do a source transformation from a voltage source to a current source? We just use Ohm's law. So V divided by R equals I. Well, V is 14.48 volts and R is 187.21. So that means I is going to be 77.34 milliamps. And here's A, here's B. This is the Norton equivalent, and this is the Thevenin equivalent right here. So now I'm asked what value of RL, that's this resistor, what value of RL would dissipate the maximum amount of power possible in this circuit? Well, we know what the maximum power transfer theorem says. It says that in order for RL, that's this one right here, to dissipate the maximum amount of power possible in this circuit, it has to equal this right here. So RL should be 187.21 ohms. So if this were some sort of a resistive filament or something like that, that you actually wanted to dissipate a lot of power, you would want it to dissipate the most it could. And so we just use the max power transfer theorem there. All right, that's it for this video.